Okay, so welcome everybody. It sounds like we were on mute here for a little while. So as you did not hear me say, we are actually going to take a little bit of a departure from our previous series where we were doing Raven, just focusing on Raven software. And today we're actually going to talk about COMPRO. And so this is our full finite element software package that builds upon the same capabilities that Raven has. Much like we have done in the past, we'll have a little introduction, a bit about the presenters and Convergent, and then we'll jump into the technical, which will cover actually the introduction to COMPRO and then advanced simulation capabilities. At any point, if you have questions, you can type them into the host, which is going to be me, and you can take those into the chat window, and then we'll have a little Q&A session at the end for about 10 minutes there. There's also an opportunity to send questions in after the fact if you don't think of them at this time. So we'll have some information about that. And so this is Alison McKee talking right now, and I'm the Analysis Applications Group Lead here at Convergent, and I'm going to be the host today. For the presenting, it's going to be Dr. Alireza Fergani. He's the engineering lead for numerical methods here at Convergent. He's been with us for 6 years, and previously he was a research associate at Composites Research Network, which is affiliated with University of British Columbia. He is also an adjunct professor there as well. And he is the master of all things numerical here, all of the equations and the science behind our software. So the outline today is this. These are the topics we're going to cover. So the introduction to Convergent, and then we're going to go over an overview of the physics-based approach to process simulation. This really talks about the theory behind what our software does, and then we'll go into an actual sort of the COMPRO in ABAQUS and ANSYS. These are two finite element packages that it is a plugin for or works in. And then we'll talk a little bit about the advanced simulation capabilities. And these are really to build upon the basis that you might know for Raven, where these capabilities can go with more complexity, but more advanced physics that can be simulated and what you can get out of that. So I'll go through the intro to the Convergent. And so, who are we? We talk about efficient composites processing, but really what we're trying to do is reduce risk, shorten development times. This is really giving you the tools to lower your costs through simulation and limited experimentation versus all experimental work. Convergent here in Canada was established in the late 90s, and we actually have 2 offices here with over 25 employees. And we are the original developer of this simulation software and also hardware products to complement your processing manufacturing processes. And we do consulting engineering here, materials characterization. We create the software here as well, and we do a lot of other consulting and training work as well. In 2015, we also established an office in Seattle, and this is a standalone company, and they're a developer and reseller of all of our tools and services. And so they do much of the same work, and they are a U.S. entity, and so you can go to them for much of the same work as us. They also do some of their own tools and integration within our framework as well. This is just an overview of our selected academic, software, and industrial partners. And so you'll see some of these listed on our website as well, but we do have quite a big academic and research partner group, the software packages that we're actually integrated with, and then a selection of the aerospace and composites manufacturing companies around the world. And you've seen this slide before if you've been in some of our webinars previously, and what we really focused on was Raven in those ones, and that's because it's fast, easy to use. It's one of the most accessible products that we have. COMPRO is really a supercharger for your finite element packages, and this is really built upon the same engine that Raven has. It's the CCA framework behind that. and we're going to go through today all of the things that you can accomplish with that. We do, as I mentioned, have engineering services. This is us running all of these software packages for you. We have materials characterization and software for that, which is the inputs to all of these simulations. And then we have hardware projects, most famous of those being our Coho vacuum leak detection. And this not only provides you with a process, but logs and documents all of this in a prescribed workflow. And what do we talk about with COMPRO? So this is going to be the main topic here, and it is, as I've mentioned, a supercharger for finite element packages, ABAQUS, ANSYS, OFEM, and these are different solvers. And so what we are doing is running the same simulations you would see within Raven, right? A thermochemical or stress. We wouldn't do the stress deformation, but we would do the same properties are calculated within Raven. And the reason where our plugins, we take advantage of all of the features that these finite element packages have. And so all of the latest contacts and element types, all of these are taken care of by these packages, but we take care of the material properties. And this is already integrated in with several workflows. And what would you do with this? The main workflows that we see people day to day is bring in, so tooling compensation, thermal profiling compliance, so checking exotherms and even cure cycle design, checking your dimensional conformance for specifications, and then really it is a tool for, an advanced user can troubleshoot any type of process and design new processes within that framework. So I'm going to hand it over now to give a little bit of the background of the physics-based process simulation. So take it away, Dr. Annie.
Thank you, Alistair, for the introduction. All right, so good morning or good afternoon, everyone. The topic of the discussion today is an introduction to COMPRO and what it does. The physics-based framework is the basis of all of our software offerings. The physics-based is founded based on our best understanding of the phenomena and the causality of the events. And there are three things that are involved in the process of composites. There's the material that's being processed, which goes through evolution of physical and chemical process. There is the sequence of events and boundary conditions. There is the temperature applied, pressure applied, and there is the equipment, and the material sometimes interacts with the equipment. And all three need to be captured in order to have a good representation of the process and predict the outcome well. Now, looking at the thermochemical problem, this is what we have discussed for the Raven simulations before. The first step is to understand the governing equations. What's the mathematical representation of the physics that's happening? For example, in the thermal problem, you have the heat transfer, so you have to have a good understanding of the heat transfer problem and its governing equations and the parameters that are required. Then there's heat that's being generated in the material, so that's a very important aspect of the thermochemical problem. And then you have the boundary conditions that are related to the cure environment as well as the interaction with the equipment. So in order to have a good high-fidelity simulation that is capable of predicting the outcome, which in this case is the temperature in the part well, we need to have a good understanding of these bits and pieces and bring them all together in our simulation framework. And you can have the simulations at different levels of complexity and detail. In a 1D Raven simulation, you have an abstract representation of the boundary condition in terms of HECs and the true thickness representation and drill through of the coil breather, the part, and the tool. As you go from a Raven 1D representation into a 3D COMPRO representation, you bring in more details in terms of the geometry of the part and also in terms of the boundary conditions, the shapes, and all of those details that might matter. We'll discuss when you would use a 1D simulation or 2D versus the 3D? What are the features in your model that makes you go from a 1D to a full 3D? So the material properties is the key to all of this, especially in processing of the composites, because the material goes through the thermochemical or thermophysical changes. So the very key thing that needs to be captured is how does the material evolve? And that's what is at the heart of Raven and COMPRO, and it's common between Raven and COMPRO. In the case of the Thermo-Chemical Analysis, cure kinetics, for example, is the key. And we provide material characterization as well, and the material models or material concealed models, or MCMs, are in the COMPRO's common component architecture that's shared between COMPRO and Raven. And representation of the boundary condition is the other important feature. In the case of curing a part in an autoclave, you have convective heat transfer boundary conditions that's represented in both finite elements or in 1D Raven simulation using HECs. And it's very important to calibrate those HEC values. Well, you might have spatial variation of the HECs depending on the placement of the tool and part in the autoclave. And the finite element tool, the 3D finite element, allows you to incorporate that spatial variation as well if from one side of the part to the other side you have a change in your HEC that can be incorporated. Now, in terms of our software offerings, we in the previous webinars we talked about Raven and showed you workflows in the 1D analysis specifically. So Raven can do ZOD, which is the material point response analysis. That is, if you provide the temperature cycle, it can give you the properties of the material as it evolves through the cycle. That's the visual testing, basically. The 1D analysis, that's thermal drill-through analysis. You represent the material as it goes through the thickness, the tool and the part and the bag or breather on top of it. And the reason that a 1D works well because the gradients in a thermal problem are mainly through the thickness. And then Raven can do some limited 2D analysis. We have some templates that are available, some flexible and some fixed templates that can be used to do some limited 2D analysis. COMPRO starts with 2D and it's extended to 3D. And it's applicable when you have very complex geometries and spatial variation of your HECs, of the temperature, or in the thermomechanical analysis when you're trying to predict the springing, when you have complex features and 3D features in your part, then you have to choose the 3D analysis. So Raven can do 0D visual testing, 1D drill through, and some limited 2D. COMPRO starts from 2D and goes to 3D. There are three basic types of simulation that you can do with COMPRO. There is the thermochemical analysis. The goal of that is to predict the temperature history at every point in the part. As a result of that, the outcomes are the thermal lags in the part, and the exotherm, and the thermal gradient. So anything related to temperature and degree of cure evolution in the part and its gradients in the part can be predicted. You can also look at the, for example, the TG of the materials when it reaches CG as well, or gelation. All of the things that are related to the thermochemical features you can get from thermochemical analysis. The second type of analysis is a consolidation analysis. So as the part goes through the application of temperature and pressure, the part gets consolidated. The volume fraction of the part might change, especially if you have spatial variation of the pressure that's applied due to use of a call sheet, for example, and the geometric features in your part. The combination of the two can lead to pressure gradients in the part, and that can lead to variation of the volume fraction, formation of porosity, gaps, and wrinkles. These are all pre-gelation regimes, the consolidation, formation of wrinkles, and porosity. So that is the focus of the flow compaction. The last one is the stress deformation, and that's probably what COMPRO is most famous for, is the springing calculation. So looking at evolution of residual stresses in the part, and from that, as you remove the part from the tool, it springs in, it warps, and the residual stress is built in. And stress deformation analysis, the goal there is to capture all of these features that lead to residual stresses and deformations after removing from the tool. These are the three basic types of simulations that COMPRO can do. Going into the thermochemical analysis, in COMPRO you can have a full 3D representation of the tool with all the details. As you see, the substructure details can be represented, and the parts can be represented. As I said, if you have a spatial variation in your HCC, you can incorporate that. Say the air flows from one side, so you'll have higher HCCs on that side, and then on the back side you have lower HCCs. All of those details you can incorporate and set the problem up in full 3D in ABAQUS or ANSYS environment. And the outcome will be the thermal lag. So, looking at the temperature lag of every point on the part with respect to the air temperature or the prescribed cure cycle. You can look at thermal gradients between both part and the tool, and thermal gradients are one of the drivers for residual stresses. You can look at, what is the temperature difference at 2 points in the part, that is the thermal gradient. And also exotherm, you have a spec that defines the boundaries of the temperature. By predicting the exotherm in the part, you can compare that with the specs. And the tools that we have within the COMPRO CAE plugin for ABAQUS helps you to look into these outcomes as well. Going into the Flow-Compaction Analysis, as I said, it applies to the pre-gelation regime. You apply the temperature and pressure, materials, resin viscosity drops, it can flow. Now, if you have pressure gradients due to geometric features or due to application of a call sheet, apply drop-offs, all of these features can cause pressure gradients in the part, and as a result of that, resin can flow. The outcomes of this simulation can be looking at the volume fraction variation. Where you have higher pressure, you would expect higher fiber volume fraction because you'll get higher consolidation. But if resin migrates into low pressure areas, usually there you have a higher resin volume fraction and lower fiber, and those areas are more prone to porosity. So by looking at some of the outcomes, like the resin pressure, that can be an indicator of defects like porosity. Thickness change is another feature that this consolidation simulation can predict. And also, as you see in the advanced simulation, wrinkling that happens during the consolidation phase can be predicted using the Flow-Compaction Analysis. And the last one is the stress-deformation, which is calculating the residual stresses that form in the part due to multiple phenomena and effects. There is the CTE mismatch between the fiber and the matrix. That's the first cause of residual stresses. You have CTE mismatch between tool and the part. The tool, if it's made out of aluminum, it wants to expand. That can lead to some interaction between tool and part and residual stress. It very much depends on the geometry of the tool and the part. Then you have the cure shrinkage of the resin, especially as the material gels and cure shrinkage kicks in. That will lead to formation of residual stresses because resin wants to shrink, fiber doesn't want to shrink, the tool doesn't want to shrink, so that fight between these components will lead to residual stress. All of these can be incorporated in the 3D simulation using COMPRO. In terms of representing the material stress evolution and modulus, there are different frameworks. There's the linear elastic, cure hardening linear instantaneous linear elastic or child approach, which for each step it assumes that the resin behavior is linear elastic. Or you can go more advanced into pseudo viscoelastic or full viscoelastic representation of the material behavior, depending on the cure cycle, if the material devitrifies during the cure cycle or how complex the cycle is. You can choose the right type of simulation. The outcome of the stress deformation simulation is basically the spring-in. The deformed shape of the part as you remove it from the tool. And all of the effects that we talked about will contribute to that. And you can use the workflows that are well established within, say, CATIA and ABAQUS framework or ANSYS framework to take the deformed shape back and redefine or redesign your tool surface to compensate for these deformations. So that with the compensated tool, the geometry of the part that you get after removing from the tool is what you want and according to the specs. At the heart of all of our software is the COMPRO's Common Component Architecture, or CCA. That is all the material constitutive models that are built into all of our software products and offerings. So this is a flow chart of how the CCA works. You have your finite element solver that can be ABAQUS, ANSYS, or OFEM. Those finite element solvers usually call some subroutines, where basically COMPRO is called. And inside COMPRO, you have this library of all these different models. There is a cure kinetics model, the resin modulus model. Depending on the type of the analysis that's being performed, the appropriate material constitutive model, or MCM, is being called and incorporated in the calculations. We have a very large library of models, more than 34 cure kinetics models, more than 23 or 4 resin modulus models. So it's a very rich library of material constitutive models that incorporates a lot of models that are available in the open literature, and some of them that are available that are developed by Convergent. And the equations behind all of these material constitutive models are available to all of our customers, so you can look at the equations, the references to the papers, if they are coming from literature, that you can look and study and see if it's applicable to your case or not. So it's very transparent at the CCA level. All the equations, all the material parameters are available to the customers. Now, in terms of the platforms that COMPRO can work on, we have COMPRO for ABAQUS that's been around for almost 15 years now. We have a graphical user interface for it, and it supports all the types of analysis that we do. And it supports, in terms of multiprocessors, it supports both SMP and MPP. That means that you can use multiprocessors on your own computer on the workstation, or you can use hundreds of clustered nodes to run very large problems. So it scales very well for large problems. There are some details in terms of the type of elements. For example, layered composite elements in ABAQUS, we only have that for stress deformation analysis. And COMPRO for ABAQUS is very well integrated into the Dassault Systèmes CATIA to ABAQUS workflow and the tools that they have. Then we have COMPRO for ANSYS that was developed almost 5 years ago. The graphical user interface for COMPRO for ANSYS is still in development, but hopefully soon, within the first quarter of 2020, we'll have it released. It can do all the types of analysis that COMPRO and ABAQUS can do. It only supports SMP right now. That means that you can run it on your workstation with multiple CPUs, but right now it doesn't support running on a cluster. It's very well integrated with ANSYS Workbench. I have a few slides on that. The Composites pre- and post-processor in ANSYS Workbench, or ACP. And you can have this the spring-in and tool compensation all done within the Workbench framework. Then the last member of the COMPRO family is OFEM. OFEM is an open source solver, and that's we're building COMPRO for OFEM framework as well. In terms of the graphical user interface, the plan is to have Raven as the preprocessor. Right now, it's quite limited what OFEM can offer in terms of the process simulation, but we're working on increasing the capabilities there as well. All right, In terms of COMPRO for ABAQUS, it's been around, as I said, for 15 years. We have a graphical user interface that's designed to guide the user through the steps of selecting the material, setting up the problem, and submitting and visualizing the results. So all the steps that used to be very tedious, it required going and editing the input file. Now it's all automated, and you define basically one setup, and in the background, the CAE plugin, depending on the type of analysis that you want to do, Thermo-Chemical or Flow-Compaction or Stress-Deformation, creates the input file, runs it in the background, and then you can visualize the results all within this CAE plugin workflow as well. So the tabs, you start from selecting the material, selecting the analysis type and analysis steps, and then submitting the job and post-processing. It guides you through all the steps, and it's very well documented. So if you look at our instruction manual, it's very well documented, the steps that need to be taken to define a problem and solve it. This is the workflow of integration with the Flow Systems tool. You start with a geometry definition, a surface definition in CATIA, and you have your layup information defined in CATIA. There is the Composites link product that Dassault Systèmes offers that will bring that information, the surface information and the layup information into ABAQUS. Then inside ABAQUS, there is the Composite Modeler software or plugin that's again offered by Dassault Systèmes that will help you build the 3D representation of the part from the surface definition and the layup. So if you have a quite complex definition of layup and ply drop-offs, that tool can be very useful to build the 3D geometry and use the 3D geometry in COMPRO to do all the calculations. Then inside ABAQUS, the CAE plugin is used to help you guide through selecting the material, defining the boundary conditions, and running the simulations. And COMPRO in the background takes care of all the calculations. At the end of a springing calculation or stress deformation, you have the deformed shape of the surface. Now, if you want to bring it back into CATIA environment and compensate the tool, there is the Realistic Shape Optimizer or RSO plugin for CATIA that can be used to bring in the deformation vectors from ABAQUS and morph the surface of the tool to the negative of that deformation to get a compensated tool surface. So very well integrated within the Dassault Systèmes offering in terms of the software. COMPRO for ANSYS is integrated into the Workbench. The mentality is quite a bit different between ABAQUS and ANSYS. So the Workbench is the environment that shares the data between these different components of analysis. You can have components that defines your geometry, or if you use ACP, the Composites Pre-Post in ANSYS, that is similar to the Composite Modeler in ABAQUS, where you can go from the surface definition and the layup into the 3D representation of the composite. And within the ANSYS Workbench framework, you can share the geometry between the different types of analysis. You see the same tool and part is being used for the Thermo-Chemical, it's called transient thermal. The second one is the Flow-Compaction, and the last one is the Stress-Deformation. So you can take advantage of all these automations and sharing the information and data within the ANSYS Workbench framework. As I said, it's compatible with the ANSYS Composite Pre-Post, ACP, as well as Space Claim in ANSYS. And you can perform the tool computation within the Workbench framework as well. You can bring back the deformed geometry, and if you have the geometry definition within the Workbench, you can compensate for it within the Workbench as well. So everything can be done within the Workbench framework. An example of a Thermo-Chemical Analysis here, an L shape, looking at the degree of cure. So it supports, as I said, all the three major types of analysis that COMPRO can do. Now, going from the traditional three basic type of simulation, thermochemical, consolidation, and the stress deformation, into more advanced simulation. So you can use COMPRO as a framework for process simulation, and especially looking at these effective or prediction of defects can be done using COMPRO as well. One of the advanced type of simulations that can be done using COMPRO is the integrated flow stress. That the aim of this kind of simulation is to predict porosity in the part. And two different major contributors to porosity can be incorporated, which is the bubble growth due to, say, moisture diffusion, or the gas that's trapped during the lamination process. So the bulk factor, all of that can be incorporated to predict the porosity of the part. There are some publications on these new features that we can share with you if you're interested in, say, predicting porosity using COMPRO as well. The other one is the deposition processes. We know that a lot of defects that we see in the composite have roots in the deposition process. It can be the AFE process or the forming process. Fiber misalignment features can happen during the deposition, and those usually continue to exist in the part all the way to the final product. So it's very important to be able to predict these deposition defects, and one of them is AFE. These capabilities were developed under NASA's ACP program. You see a video of an AFE deposition process here. In the AFE process, there are the drivers for formation of wrinkles, as you see in the video. That is, a steering around the radius builds in residual stresses in the part in the toe that leads to wrinkles. There is the resistor, that is the tack between the deposited toe and the substrate, and we have tack models built in to COMPRO and also Raven that can predict the tack behavior. The next example in terms of the advanced simulations is the forming process. So in the forming process, the material goes through very large deformations and rotations, and you have a very complex interaction of the forming apparatus, the tool, and the part happening, and the wrinkles happen due to the excess length that exists in the part. So the key here is to be able to cope with all those large deformations and predict the excess length that leads to wrinkles, and also mechanisms like shear deformation that relieves the excess length needs to be predicted as well in order to predict forming. Again, we have publications on the forming as well. If you're interested, please contact us to share those with you. Similar to forming, consolidation-driven wrinkles is another defect that happens in the pre-gelation regime. You see a corner consolidation video simulation that's happening right now. On the top surface of this corner, you have excess length. If it's not accommodated, if it's not released, it will turn into wrinkle formation, and COMPRO can be used to predict those. Other features that can be predicted are corner thickening and corner thinning that can happen due to the pressure gradient in the part at these different geometric features. All right, another type of simulation that can be done all within the same COMPRO CCA framework is simulation of additive manufacturing. Over here you see deposition of the peak material and looking at the temperature evolution on top and degree of crystallinity evolution at the bottom. Some of the features of the material models, for example, in thermoplastics, the crystallinity models, the melt models, the induction time models, that all play key roles in an additive manufacturing process to set different process conditions, the temperature, the rate of deposition, the base temperature. All of those can be simulated virtually using COMPRO and avoid many iterations to achieve good quality parts. Theory-guided machine learning is one of the new features that's coming into our product. This is to accelerate the simulation process. It can be used for optimization to find the optimized cure cycle. We're incorporating that into Raven framework as well as our CPA-TA framework. And the last one is probabilistic representation. This is, I don't think it's released publicly yet, but it's coming out, it's in the pipeline. The idea here is that there is variability, there is inherent variability in the material. There's also errors in measurements as you characterize the material. The idea is to incorporate those variabilities and predict, for example, in this case, the temperature, given the variability, that inherent variability in the material and measurements, and propagate that through the simulation, in this case, to predict the temperature of the part as well. So instead of having one analytical solution that gives you a single temperature, it gives you a distribution of the temperature predictions as well. All right, so that was the slides that we had for today. Please feel free to type if there's any question in the chat box. I would be happy to answer them.
Yeah, so you can, thank you, Ali Reza, and so you can type any questions that you have now, and of course, if you don't think of any immediately, we can email us here at info@convergent.ca, and I will remind everybody we will have another webinar next month, at the end of the month, and this is actually going to build upon what we presented today, and actually go through a workflow example with COMPRO. I think this should just show everybody a little bit more of what would be required to do so. So while I wait for people to type in a few questions, there was one that had come in partway through, and it was, I think we partly answered it along the way, but it was, do I need ABAQUS or ANSYS to actually run COMPRO? And I can answer that one. And so we would say yes, there are capabilities coming out in OOFEM in the future, and that's a little bit more integrated with Raven. But yes, it is. You do need a finite element package to run the full 3D models there. And so one of the questions was actually related to some of those advanced simulations and the ACP, the AFP, additive manufacturing. And so are those integrated with, like are those publicly available with the COMPRO, that anybody can buy right now?
Right. So the capabilities are there, but in terms of streamlining, for example, in the case of AM, you have the deposition that's happening. That means that the elements need to be activated, and that's not automated yet. So there's some manual steps that needs to be done. What COMPRO provides there is the response of the material. So as the material is being deposited at temperature that's above the melting temperature, so it comes in at the molten stage, and then it cools down, the crystallization starts to form after the induction time. All of those features that are related to the material response are being simulated using COMPRO. But in terms of the workflow of setting up the simulation, having the elements activated, that's not automated. So it's right now it is a manual process, but it's doable.
Right, and actually, I was going to add upon that, and actually there was a question about what materials are available in that. And so, one of the things with any of this simulations, you require different inputs for different types of analyses, and in some cases, some of these advanced simulations do require more detailed, more advanced characterization to go in. And so, that's something that Convergent does, and we can work with customers to actually get all of the inputs required for any of these simulations, and it's not necessary that we also do it. People do this themselves as well. For the NASA program particularly, are some of those materials going to be made available?
It needs to be decided by NASA.
Right. Okay, and so just given the time, we're right up against the cutoff time, so I'm going to, we'll follow up with any of the remaining questions here after just privately. But I thank you everybody for attending today's webinar, and we'll join you in about 1 month.
Thank you very much, everyone. Have a great day.